Dominik, I know that the whole effort is a collaboration between the Google Fonts and the Chrome team, but you're on the Chrome team, right?
I'm on the Chrome team.
Yeah, okay. I need to keep this straight. I'm always disproportionately excited about foundational technologies that other stuff gets built on, because these building blocks have a big long-term impact on the typography and fonts landscape. And so I'm actually quite excited about Dominik's work. You know, the stuff you're doing is for Chrome as the initial client, but it has being open source anybody for.
Thank you, Thomas. Thank you to the conference organizers for inviting me here today. The topic of my talk is crafting new fontations for Chrome. As Thomas explained, I'm on the Chrome team. I'm at Google for about 8 years. I worked on browser typography for about 15 years in total. Before this, I've worked on variable fonts and integrating that with Chrome. And I co-developed the Color V1 specification and also worked on integrating and shipping that in Chrome. So let's dive into this talk. As Thomas also said, this is a talk about crafting new fontations for Chrome. In the Google Fonts and Chrome team, we're working hard on a change that's hopefully invisible to our users. I'm going to show you 2 screenshots. And you can see if you notice any difference. We hope you won't. I can tell you there are tiny differences that we work on even removing. So let's take a look. Here's the ATypI website, snapshot in Chrome. And this is what it's going to look like. And here's what it looks like at the moment. So is this an unnoticeable change? When using the browser and showing text using the web and fonts embedded in a page, no change is visible here. So why are we doing that? Why are we spending so much engineering effort and 2 teams working on this at Google? Behind the scenes, a foundational change is happening. We're changing the way that text and fonts are shown on screen, and also how we produce them and compile them and kind of change the production pipeline in Google Fonts. So the change is foundational, and that's why we call the code that we're working on Fontations. If there's no visible change, why do we do it? We do it for 2 reasons. One reason is to improve font security in Chrome. And in this talk, I'm going to do a bit of an excursion into what software security is and why this is important for you as users of Chrome as well. And the second reason is we want to improve font production performance and velocity for Google Fonts. So let's dig in a bit deeper. I'll explain what it is that we call fontations, how we use fontations to improve font security in Chrome, and how fontations helps us accelerate performance in font production. I have some numbers and examples on that. And lastly, how do we gain engineering velocity from using fontations and sharing the same set of libraries between Chrome and Google Fonts? So what is Fontations really? It's a set of secure, modular, high-performance software libraries to parse and render and to create font files. It's open source, and you can find it at this address on GitHub. It consists of several components, keeping a modular architecture and useful building blocks for almost any type and font processing tasks. I'll go through these modules that are part of Fontations. First, it's font types. As the name says, general types mostly closely mapping the OpenType standard. Read fonts is a code-generated zero-copy parser for font files. Zero-copy means we don't copy the contents of the font file to an extra region in memory to kind of do secondary processing on it, so it's quite efficient. And a second characteristic here, It's using generated code, so the parser is not written manually. It's building on years of experience from Google Fonts and their work on the Python font tools. Skrifa is the next level. It's a higher level font processing functionality. That means glyph scaling, variable font interpolation, hinting and auto-hinting, and color font rendering. And these are the parts that we can use in Chrome, and the next bits is write fonts. That's more related to font production. So library for creating font table objects in memory, adding information to them, filling them with information, and then writing them out to disk as serialized font files. Font CodeGen is mentioned here as a model, but that's not really meant for external consumption. It's more like an internal tool, part of Fontations, how we go from machine-readable definitions in a way like a machine-readable form of the OpenType specification and generate parsing code out of that. So we arrived at this set of modules by learning from past experience with FreeType and fonttools. These are both libraries that Google invested in and developed or helped develop before. And these two libraries perform similar tasks. They also process font files, they help in rendering, or they help in font production. fonttools and varlib are written in Python, and FreeType is written in C. And the choice of programming language is something that's important in this context, and I'll go a bit into that later. With Fontations, we aim to surpass fonttools in performance and surpass FreeType in software security. Google Fonts previously moved subsetting from Python to native code and found great speedups. So Google Fonts did subsetting in fonttools first, and then later developed the subsetting part of the functionality in half-bus and saw great speedups. So we're hoping for similar or better speedups when we move from Python to native code for a couple of font tasks that we use in compilation and in a kind of production of font projects that Google Fonts maintains. So what are we doing differently to FreeType and fonttools before? We're using code generation versus manual parsing. By means of code generation, producing parsing code is no longer a manual and slightly error-prone task with handwritten parser code, but it becomes partially automated and less error-prone and easier and more robust to change and amend in the future. And we're taking a very modular approach. We keep parsing separate from higher-level processing. Font parsing is in its own module, and interpolation, scaling, and all these are in a separate higher-level module. So depending on what you need, whether you need to modify really the lower bits of the font, you can use that library for it. If you want to rasterize display fonts, you can use like the higher level functionality that's in Skrifa. We have these different APIs and functionality in separate interfaces, and we separate them more. For example, in FreeType, all the functionality is on the ft-face programming interface object, but there's low-level to high-level functionality all in the same API, but we keep that a bit more separate because we have, depending on context, different use for it. We are also applying one learning that we have from implementing Color V0 and Color V1, and it turns out that we don't need to use the FreeType rasterizer for example, Color V1 display. So in the set of Fontations libraries, there's no rasterizer in it. Perhaps I should say yet, but we're using Skia as the 2D graphics library for rasterizing. So Fontations only gives you the contour data, and we do the rasterization in separate steps. In the introduction, I explained we're building Fontations for reasons of software security. Let's go to some detail of why that is important for Chrome and what software security around fonts means. Chrome prides itself to be a very safe browser. If you go to the safety.google information, you'll see there Chrome is secure by default. But how can we keep that level? How can we raise the bar, and how can we make software that processes font files safer in the future? And what does it mean in practice, and what does it mean when something goes wrong with software security when it comes to fonts? Let's start by talking about what a malicious font is. And how could a malicious font cause harm? It's a font file that's intentionally malformed with the intention of executing harmful software code on your phone or PC. Such a font is intentionally crafted to break into a user's browser and is different from a font that is intended to display correctly. There's no type designer involved in making a malicious font. There's more like a software security researcher or an attacker involved in making that. A malicious font is harming or harmful by exploiting weaknesses in the code that processes font files. It changes program execution and makes the attack device run code that the attacker controls. So in order to protect Chrome users against such attacks, we run automated systems to try and find such software vulnerabilities before any attacker finds them. These systems are unfortunately, at the moment, not 100% bulletproof. And in 2020, we learned that there were malicious actors actively exploiting a font vulnerability in Chrome. So this happened 3.5 years ago, in October 2020. Our colleague Sergey Glazunov of Project Zero, which is a software security team at Google, found an actively exploited bug. That means he found activity on the internet where someone was trying to break into Chrome using a malicious font file. This bug was a software security issue in the FreeType library. When the fix was rolled out to users, then there was more information available about what this issue means or what the font actually did. And this came out long ago now in like Chrome version 86. Now we're at like 124, roughly. So the issue was picked up by security blogs and some news sites, and they reported on this. So of course we don't want that to happen, that there is something that Chrome is vulnerable to here. So we want to raise the security here and make Chrome safe, even when someone tries to break into it with a malicious font file. And with Fontations, attacks through font files will become a whole lot harder, and a whole class of security issues will be eradicated. We found a fix for this security issue in FreeType, and we took measures to improve finding such software securities in advance. But we also noticed if we keep finding them, we spend a lot of our engineering time on fixing them and so on. So we thought, we started tracking the numbers, and these numbers give us an indication of how well we do in terms of security in our code that processes fonts. These numbers showed us we can do more here. It also showed us, as I said, like how much engineering time we're spending. So we analyzed the reasons for why our systems were informing us about many potential security issues. Here you see some numbers over a period of 2 years. And one of the reasons was our font library FreeType is not written in a safe programming language. It's written in C, and it's vulnerable to memory safety and other software stability issues. How can we address them, and what would be the solution to this? We won't succeed fixing all bugs in the C library, so we need to switch to a different, more modern language, which gives us safety guarantees around these memory safety issues. So we wanted to move away from C and switch to a new programming language that's memory safe. And that software language is called, programming language is called Rust. Rust is a programming language with safety kind of built into the design. So and with Rust you can write code that's memory safe and is not vulnerable to these issues that we saw in FreeType. Memory safe means when writing programs in that language, typical memory safety software vulnerabilities are ruled out. If we would rewrite our font processing in this language, we would be addressing all of these issues that we saw in FreeType. And research on Android makes us optimistic that we can, in fact, remove this whole class of issues in the font code. The link here on the slide leads you to a blog post where Android engineering is showing their findings about these types of rewrites in the new language. And these findings were coinciding with Google Fonts' efforts into making their font production more efficient. And that's a project that Google Fonts started calling Project Oxidize. So they wanted to make their font production faster. For reaching these performance goals and for improving their developer productivity, they also considered Rust as the programming language. So the Google Fonts team and the Chrome team joined together and set about developing Fontations and the integration to Chrome together. So what does the integration of Fontations into Chrome look like? Blink is Chrome's rendering engine. And in the rendering engine, we use Skia for graphics processing and font processing. And in that stage of font rendering, we use multiple backends, what we call them. So on Windows, for example, we use direct write for rasterizing and rendering most of the fonts. On macOS, we use Cortex for that. But on all our other platforms, for example, on Android and on Chrome OS, we use FreeType, or we used to use FreeType. And FreeType is what we're going to replace with this safe alternative, Fontations. So when do we use FreeTypes and when do we use FreeType and when will we use Fontations? By default, we would usually invoke the system font rasterizer, Cortex or direct write. But when there is, for example, the font that we want to display is a format that the system rasterizer doesn't support, for example, a CFF2 font or a color font, then we invoke the backend Fontations, or currently FreeType, but this will be migrating to Fontations. And if the system, in the case of Android and Chrome OS, the system rasterizer is Fontations directly. So this was the kind of in-depth explanations of how we're using it in Chrome. But let's explain how Fontations also changes what we do in font production. And let's take a look at what we gain there. In terms of the different modules, or crates as we call them, the write fonts module plays an important role for font production. Write fonts is the basis for a successor to FontMake. And by using Fontations, we're seeing tremendous speed-ups of at least 10 times the speed. For example, for one internal project that Google Fonts is working on, they gave me some numbers that the compilation time of compiling this font project from the sources to the final font binary is going down from 1 minute and 47 seconds to 9 seconds. So that increases the throughput a lot, and that makes it easy to kind of tweak the font, change it, recompile it. Instead of waiting for 2 minutes, you can do that almost instantly. And the Rust, or the choice of programming language, helps making this compilation process faster because we can parallelize more of the tasks that are executed during compilation. So here's an example just to demonstrate that this is already available and kind of similar in API perhaps and usage to fonttools. So if you write a new bit of Rust code to modify the last modified timestamp of the header table of the font, then this is what it would look like. We read the font from a file, we pass the head table, then we change the modified date in the head table, then we make a new font builder, add this modified head table, and fill in the other tables from the existing parts of the font, and then write it out to the file system. This is a basic example, but this is how kind of read fonts and write fonts collaborate. So you pass first, you make modifications, you write it out. So we've seen the two major applications of the Fontations library in Chrome for font rendering, and in FontC and FontMake, or sort of FontC as a successor to FontMake in the Google Fonts production pipeline. Let me talk about the velocity we're gaining when these two use cases run on the same stack. Because we now use the same Fontations library as a foundation in Chrome and for Google Fonts production needs, we are faster at innovating in the font technology space. When we bring 24-bit glyph IDs to our font stack in Chrome, the changes need to be made only in the underlying Fontations libraries. Or if we wanted to bring, let's say, a blur filter to the color V1 color font format, the required changes, again, would only need to be made in Fontations, and they help in font production and in font rendering at the same time. Or when starting implementing variable composites or cubic Béziers in the glyph table, which are on the way into the open font format specification, again, we only need to change that in Fontations, and we have support for it in the font production and in rendering. We no longer need to have separate implementations for font production, such as in fonttools and FreeType, but we only make changes once. So besides these gains in velocity by using the same library in two tools, we get velocity from building in Rust itself. It becomes less risky and to modify and maintain complex font processing code. There's a lower risk of breakage, and there's close to no risk of introducing new memory security issues. In our teams, we can confirm the observations that Lars Bergström, director in Android engineering, is explaining. After an initial learning phase, we are more productive writing code in Rust than in C++ or definitely in C. Finally, all of this is something that you can try out, and I think I have a few minutes to try a short demo as well. So if you download the very latest version of Chrome, what we call the Canary version, then you can go to Chrome flags and say enable Fontations backend. And then if you run this on a platform, for example on Android or on Linux or Chrome OS, and you go to Chrome Developer Tools, then you see here that at the bottom in the DevTools window of Chrome, you see that when a particular font, when you select an element on the page, it shows you that this particular font is rendered through Fontations. This is all still a preview, but this is one way of kind of testing this out. At this point, I want to say this has been, of course, a team effort. Various teams involved, the Google Fonts team, the Skia team, the Chrome team. In particular, I would like to call out Röttsches and his team from the Google Fonts for their work on the Fontations libraries, and Ben Wagner from the Skia team for his help with integrating that into Skia. I can give a small demo, I think. Let's see. Yes, so what I was mentioning, here's the Canary version of Chrome. This is version 125. This is not the current stable version. And here I've enabled Fontations. And what you see here is one very unreadable font, I would say. It's a color V1 test font that I made. So here's a couple of tests for sweep gradients in color V1. And when you go to DevTools here, you see that this is now using Fontations. And it's already kind of displaying this. I'm using a color font because this is one of the fonts that's not natively supported by the system rasterizer. If I would use Chrome on Linux, then all of it would run through Fontations. But yeah, here you can test various graphics primitives of the color V1 fonts and change the variable coordinates and so on, and that's all going through the stack. And this is, to my knowledge at the moment, free of software security issues in the font parsing and font processing code. Yes, so that's all. Ready for questions.
So thank you so much, Dominik. For those of us who are more on the creative end of this, this may have seemed extremely technical and even dry, but I just wanted to point out that one of the uses of this library is in processes that do font compiling as a replacement for
Font make.
font make, which is used in all sorts of things. And what that means functionally is, well, let me put it this way. In tests that I've seen of some of the modules of Fontations, you might get, say, maybe 100 times speed up.
It's possible. Like we
Yeah,
definitely.
I've seen actual benchmarks where they were building fonts and they were building in 1/100th of the time. So something that used to take a minute and a half takes less than a second, and that is like a significant font developer benefit for sure. For me personally, I will add, I have a process right now that I have to run weekly because I do one big task for Google, which is build and maintain their variable icon fonts. And on my heavily loaded M1 MacBook, the weekly build took an hour and a half, which is fine usually, but sometimes there's an urgent bug that needs fixing and people waiting. Anyway, and now I've got down to 45 minutes on the most tricked out M3 MacBook with 128 gig of RAM. And I'm just waiting for the last touches to be put on this so that I can switch over and bring that down to like real time, and I'll just sit there and wait a minute and it'll be done.
Yes, that's what we're trying to achieve with that. Yes.
Exactly. Anyway, I'm sorry. This is just dear to my heart because it's a pain point in my everyday life. Any questions out there in the audience, though? Jason.
Well, naturally, I'll bring it back to web stuff. But I think that it was at the very end of your talk that it was a bit of an aha for me about what this will mean for stuff on the web. And I'm wondering if you can talk a little bit about how this would interact with something like incremental font transfer. Are they going to be sort of, do they do different things, or will this be a sort of like a multiplier on making things faster on the web?
Yeah, it's a good question. Let me think. So I think definitely incremental font transfer is, I think, on a slightly higher level than this, but where we think, so incremental font transfer will chop up the font, make it faster to kind of augment the font in various pieces when you download them to the browser. And that's where we need the safe processing. So in a way, it will make incremental font transfer safer as well, because with incremental font transfer, the sort of processing of fonts is multiplied, right? Like you process and decode fonts much more often with incremental fonts. So in that sense, it plays into that. And I think generally having a flexible and safe and maintainable foundation for this makes it easier to bring incremental font transfer to the browsers as well.
Right. Huh?
So hello, I'm wondering if one day we can have an access in the web that we can actually read the metadata of the font, like the metrics or the name table, etc.
What was the first part of your question?
So my question is, I'm wondering if one day we will have an access, like in the browser on web, via CSS or JavaScript to get the metadata, like some metrics or the name table of a font. Would it be possible in the future?
Good question. So, like, I think there are two parts to the answer. One would be exposing the functionality that's in read fonts as a web API. From our point of view, we're not against that in a way, because we have safe libraries that have an encapsulated interface that works. But we have to kind of move the web forward as a whole, so we have to kind of discuss with other browser vendors of like, is that something we can expose and so on, and they have different libraries. But what's possible right now, you can use read fonts and compile it to WASM and then use that in JavaScript. And read fonts is relatively compact. It doesn't have a lot of dependencies, so you can compile it into a WASM library and use it quite effectively for extracting all kinds of metadata you want.
Great. Okay. Any other questions before we wrap up and move on? We still have time. Don't be shy. I guess we're done then.
Okay.
Thank you so much, Dominik.
Thank you.